All right, we're doing section 2 in chapter 4, graphing linear equations. First thing we're going to do in the chapter is finding which ordered pairs are solutions to 3x minus y equals 7. So when you find if something is a solution, you're plugging in the x value. Remember that a coordinate is always x, y. So you're plugging in the first number in for the x and the second number in for the y. So 3 times 1 minus 4, we want to know if that's equal to 7. Every time you're going to plug in the numbers. Oops, 3, not 1. Looking ahead. And that one is not. 3 times 1 minus negative 4. Is that equal to 7? Yes, it is. 3 times 5 minus negative 3. Is that 7? No, that's 18. And last one, 3 times negative 1 minus negative 2 is negative 1. So it's not equal to 7. No. So our ordered pair that is a solution is B, 1, negative 4. Okay, so let's try another one of those. Tell whether this is a solution to x plus 2y equals 5. So we're going to put the first number in for the x's and the second number in for y. I want to know if that's equal to 5. 4 plus 2 times negative 1/2 is 3, so no, this is not a solution. Okay, so graph this equation. The only way we know how to do that is what we showed in the last section where we had to plot the points using a table. So that was always when we had equations that were y equals something x. So we need to solve this equation for y. The way we're going to do that is we're going to add 2x to both sides. So our equation is going to be 2x minus 3. And then we're going to make a table with x's and y's. And the numbers that I always think are a good go-to are negative 2 through positive 2. So that gives you a good variety of numbers. Okay, you put negative 2 in. 2 times negative 2 minus 3 is negative 7. 2 times negative 1 minus 3 is negative 5. 2 times 0 minus 3 is negative 3. 2 times 1 minus 3 is negative 1. And 2 times 2 minus 3 is positive 1. So we need to go ahead and plot those points. Negative 2, negative 7. Negative 1, negative 5. 0, negative 3. We'll split that at negative 2, close one. 1, negative 1. And 2, 1. Now, in the last section, we never connected the points because it always gave us a set domain. This time it didn't, so we are going to go ahead and connect our dots, make a line. To make sure to put arrows on the end, that means that our line continues. Okay, here's a couple of definitions. A linear equation is an equation whose graph is a line. That's pretty straightforward. You graph an equation and it gives you a line. That's called a linear equation. Standard form of a line is a times x plus b times y equals c, where a, b, and c are real numbers. Okay, so notice that has the x and the y in there. That's called standard form of a line. Okay, we have a couple of different equations we need to graph here, where y equals 2 and x equals negative 1. So we're going to have a here on the left side and b on the right side. Okay, so let's find where y is equal to 2. Remember, this is the x-axis and this is the y-axis. So when y is 2, that happens right here, here. Every single one of these points, our y value is 2. Because it doesn't have an x value in our equation at all, we know that it's just going to be a horizontal line through all those points. It's very similar with the second one. It says x equals negative 1. So again, remembering that's the x, that's the y-axis. X is negative 1 here, all the way down. So this one's going to be a vertical line. So to sum that up, horizontal lines are always in the form y equals b, where some number b, and vertical lines are always x equals a. The horizontal line y equals b is going to go through where this point down here is 0b, and the vertical line x equals a is always going to go through this point, which is a comma 0. So try not to get those confused between the horizontal and the vertical lines. Graph the function y equals negative 1/2 x plus 4, where the domain is greater than or equal to 0, then identify the range. Alright, so we need to pick some points. It's already solved for y, so we don't have to do that. The domain has to be greater than or equal to 0, so let's pick a bunch of points that are 0 and greater. It really doesn't matter what you pick. I'm going to go out to 8. I'm going to go by 2s. Picking 5 points is always a good rule of thumb. Because we know that we're only picking positive x values, when I make this over here, I'm only going to include positive x values. So I just moved the axes over so that it didn't go from negative 7 to 7. Instead, it's going from negative 2 to 12. Alright, so now we plug these x values into our function. I chose even values because I noticed that there's a negative 1/2 in the function. And if you do an odd number, negative 1/2 times 1, you're going to get a fraction for your y values. So I picked all evens, which will turn out nicely. Plug all of these in for y. We'll get 4 when we put in 0. 3, and it's just going to go 2, 1, 0. If you did happen to use numbers with odd numbers, so you have decimals, just make sure that you approximate the points. Alright, let's go ahead and graph. 0, 4, 2, 3, 4, 2, 6, 1, 8, 0, and we can connect the points. We do not, however, draw a line to the left because it's telling us that our domain is only when x is greater than or equal to 0, so we're going to draw our line to the right. And I have to figure out what the range is. Remember that the range corresponds to the y values, so if you just wrote down 4, 3, 2, 1, 0, that's not going to be accurate because everyone could have picked different points. So we're going to look at what y values would satisfy this equation. Well, the arrow tells us that they go all the way down, but they don't go past this value right here, which is 4. So our range is only when y is less than or equal to 4. Okay, last one is a word problem. The distance d in miles that a runner travels is given by the function d equals 6t, where t is time in hours that's spent running. The runner plans to go for a 1.5 hour run. Graph the function and identify its domain and range. Okay, so we're going to have t, that's in hours. Make a table to pick a bunch of points. And d, which is a distance in miles. Plans to go for a 1.5 hour run. So this is a really tricky one because it doesn't give you exactly what the domain is. We just need to think about what numbers we need to put in for t. Well, we shouldn't put in negative values for t because t is representing time and we can't have negative time. So we always start with 0 when it comes to time. And we know that we want to go up to 1.5. So it might be a good idea to go by 0.5 for our t values. So 0.5, 1, and 1.5. In this case, that is going to cover our entire domain, so we don't have to do any points past 1.5. Because he only plans on going for a 1.5 hour run, he's not going to do anything longer than that. Okay, then we're going to put those t values in to our function d equals 6t. Function's up here. Okay, so you put in 0, you get 0. Put in 0.5, you get 3. Put in 1, you get 6. And 1.5, you get 9. So we should go ahead and graph this one. Again, we have to pay attention to our axes and where those should be. This is our d-axis in this case. And again, our t-axis is only positive, 0 to 1.5. So I'm probably going to make 2 boxes represent one whole in this case. 1, 2, 3, 4. Because if we just used each box representing 1, this would be a really tiny graph on this coordinate plane. And then we'd go by ones on the vertical axis. Okay, so let's go ahead and graph this. At 0, we get 3. Oops, I'm sorry. 0, 0. Let's undo that. 0, 0. 0.5 goes to 3. 1 goes to 6. And 0.5 goes to 9. So we can connect those because everything in between stands. But we cannot continue that line in the negative direction because you can't have negative time, and we're not going to extend it in the positive past 1.5 because our domain only goes up to 1.5 because that's how long his run is. We need to identify the domain and range. The domain goes with the x values of the graph. In this case, that's our t values, and we only went from 0 because you can't have negative time, and then our biggest t value was 1.5 because that's how long our run is. And the range started at 0, and the biggest our range got, which was distance, is 9. Okay, so domain and range can be really tricky on problems like this. You just have to think about context and what makes sense and what doesn't. But we can include everything in between, even though we were only using a few points because they didn't give us this is your domain, is these 3 points. So we use everything in between what we used. Okay, so that was section 2 on graphing linear equations.